Okay, perfect. So let's welcome Yuval Oreg, who will continue on this topological superconductivity topic with a tiny magnetic field.
Yeah. Thank you for the organizer for arranging this conference. We will really talk about data. And it's also the French team, application Spanish team. Okay, so today I will talk about this topological superconductivity. So Ramon mentioned the idea that we need large G factor because when you apply the key concept here was that you proximity superconductivity, you have some spin orbit coupling that rotate the spin, and then you need a Zeeman field. But in fact, when you think about it, why do we need Zeeman field at all? After all, we can apply orbital field and use the spin orbit coupling to generate Zeeman field. So we don't need this large G factor. So all talk will be about how to use material with G factor equal to 0, still with spin orbit coupling. G factor equal to 0 and to produce topological superconductivity. So that will open up a complete new set of materials. And I will show you, and I try to convince you that you can tune many different systems into a topological state, both in 1D and in 2 dimensions. Now, about 2 dimensions, topological superconductivity in two dimensions, I would like also to discuss one experiment that was done in Philip Kim group. This is a topological insulator, so it has surface of topological insulator. On top of that, they put a niobium superconductor in a Corbino geometry, and I think they saw topological superconductivity, the system, and even odd effect, and this is what you expect from topological superconductivity. I will describe that in details, and I think I will not have time to discuss something that we are working on with Javad Shabani, a group in New York. So these are array of superconductors, aluminum and indium arsenide, not in what expected to be topological superconductivity. You need to tune more parameters, but I will show you some key results that are essential to have topological superconductivity that they actually are in the right direction. This is unpublished. I hope that we will be for the top, but in forecast. So it will be, I hope. So, okay, so before I start, I apologize if many of you saw that trailer of the course that we developed at Weizmann on topological material. So there are like 50 hours of talks by our team. And if you want an introduction to the subject of topological quantum matter, this is fun to watch it before you go to sleep or in between. Still invest a lot in the so is there wow. Yeah, and we invest a lot in the so you can, it's all free, you can see it on YouTube, and you can also get, if you pay something, you can get credits for that in certain universities. So you're most welcome. This is just an introductory course. It's still not outdated, but the basics is there. So this is how it was done with director and CAD. The main point, they told us that you have too many formulas, you should yeah, but it's fun to watch, so I encourage you to do that. And these are my collaborators, so on this work, both theorists and experimentalists. So it's a summary of 2 publications of my, now is Omri, who is now doing postdoc in Cornell. This was his PhD stuff, and so I will describe for you 5 publications, summary of 5 publications for his PhD. And more recently, there are these poor men, Majoranas, but without Zeeman field, only by tuning the phases of the superconductor. And that's supposed to work in many different materials, including germanium, and systems that do not have large G factor, but just strong spin orbit cluster. And I discussed this experiment, the Corvino Josephson junction from Philip Kim. So this is the history of the subject, just related to what I'm discussing today. It is impossible to do everything. So all the proposals here demands large G factor. Besides two suggestions, one is the original Foucault idea on this topological superconductivity surface of a topological insulator, surface of a 3D topological insulator, and on top of that, superconductor. And actually, I will show you the experiment that actually implement this idea. And there was the story of the full shell wire that, at least in theory, there the G factor doesn't play any role. Yeah, and we had heard a lot about the experiments of the Pullman scaling. So before I continue, I want just to mention that this idea also related to the question that you asked. This idea to tune Andreev state. So in this work, we didn't have any Coulomb interaction. The idea was to tune the Andreev level of this quantum dot, and by adaptive tuning of one after the other, we can create a Kitaev chain. And in this Kitaev, so each point we tune the gate so that the Andreev state will form. So the two dots will form short Kitaev chain. Then by tuning with gate potential, by tuning the coupling, we can step by step produce the Kitaev chain without any Coulomb interaction. So it's possible to do that, at least in theory. The implementation was done with Coulomb, very small dot. It's possible to do it in this way. In this proposal, we had the Zeeman field, and I will show you now that it's also possible to get rid of the Zeeman field, and therefore open up for many different. So since there are many experimentalists in the audience, I encourage you to pursue this direction in new materials. It's supposed to have better numbers. I mean, the gap will be larger. That may help. There are many issues with cross-capacitive couplings between the quantum dot, which is they are absent here because there is no interaction. So I don't have to explain the negative effect of large magnetic field. It's great magnetic impurity, and this is just example of one of these. So this has nothing to do with topological qubit. It's an example of two-level system with same lifetime. When you apply magnetic field, there is a drop in the lifetime, very sharp, already 40 millitesla. So you really want to have a system with no Zeeman field or very tiny magnetic field. And so this is the main idea that I want to explain, that in fact, by replacing the Zeeman field, what we do is we use two phase differences. So in Josephson junction, we have one phase difference. That is not enough. If I need at least two Josephson junctions, and so we have two phase differences. The key idea is now to create what some people call, so this is the unit circle of the imaginary and real part of the gap in the superconductor, and this is just the phase of the two junctions, meaning three superconductors. The phase difference is in between phi 2 minus phi 1 and phi 3 minus phi 2. That's enough. So if we have this so-called discrete vortex in which the phases can go around the origin, then using other parameters, you can create a topological superconductor with Arana modes and all what we want to create. So this is, as usual, you want to explain something, you start from a toy model. So our toy model exists of 3 superconductors, so 3 dots. Each one of them has its own phase. Of course, only 2 phase differences are important. As you hop between the dots, the spinful problem, you also acquire the so-called Aharonov-Kasher phase, so spin up. In here, I limit myself because the toy model to a simple situation that spin up acquire a phase lambda as it's hop from 1 to 2 and phase minus lambda for spin down. And if you go around the ring, so again, it could be, doesn't have to be sigma z, it could be in any direction, but this is the simplest way to understand that. So now, don't show the math, mathematics, but it's pretty easy. Just you can count these 12 by 12 metrics and just solve it. And there are also some analytical part. You can show that you can, by tuning 3 parameters, the chemical potential, the strength of the superconductivity, and the spin-orbit coupling, you can create delocalized zero an Andreev state, which is not spin degenerate, which has exactly 0 energy. So you can around the ring. So this is how you create 2 Majorana modes with 0 energy, but they are not separated in space. They just sit on top of each other. So this will be the basic ingredient. Now what I'm going to do is to couple this ring either in stack or on a plane, to couple the Majoranas in different ways and form chains with end modes, or it will be a P-wave superconductor, which is gap in the bulk, and there will be an edge mode propagating in the system. So both in 1D and 2D, but this is the basic idea. No dimensions, only phases of the superconductor and Aharonov-Kasher phase that the spins acquire as they hop from side to side. So this is the example how to get that. If I stack the rings in one on top of each other, then I have this cylinder, and I can control the phase, the 2 phase differences by 2 loops, 1 and 2. So if I look at the k equal to 0, k parallel the direction of the cylinder equal to 0 mode, then this is just my 3 dots. For k equal to 0, it's just my 3 dot toy model, and as I tune parameter, k equal to 0, of course, the 0 energy, this indicate a topological phase transition. Just what happens and what we expect in this situation is to have the Majorana mode. When we create this topological phase transition, we'll have a Majorana mode here and there, and this is very similar to the idea of the full shell. So there was an experiment in Sole Pitacactus that it was a full shell, so it was an indium arsenide wire covered totally by a superconductor. There you need to put pretty large magnetic field to create one flux quantum, H over 2E in the sample here. Somehow we solved that by having these loops. So you need really tiny magnetic field in order to produce the same physics. So somehow the Josephson junction help us to concentrate, and the loops help us to concentrate the effect of the magnetic field on the junction. This is the basic idea. So this is one way to understand when we have Majorana 0 modes.
I don't get the loops. Can you show me?
Hi.
I'm not sure I remember the concentrated field.
So just imagine, okay, this is the theorist picture, but I will show you.
But in the cylinder, yeah, the geometry is tricky to get.
Yeah, so I will, that's exactly what I'm going to discuss now, planar geometry.
For people who do devices, it's
can we wait with these questions for people? I'm going to discuss planar geometry. Just the next slide. So indeed, this was kind of theorist idea. So put cylinder. You can imagine, but we immediately thought, oh, okay, all what you have here is two Josephson junctions. But it's important to have also some path to go from this junction to that one. That was the point. So, yes. So there were already discussions of standard Josephson junctions with magnetic field, with Zeeman field. We discussed experiments were made in 2007 in Copenhagen and at Harvard. But what we want to discuss is three superconductors. And the key point is this, to have this discrete properties. So how to do that? So S, N, S, and S junctions, two Josephson junctions. So when they are very far, they will not interact with each other. This will be a short Josephson junction, so you will not have spin split. The Andreev level will be spin degenerate. So this is not the situation that we want, and it does not mimic the cylinder because superconductor 1 is coupled to 2 and 2 to 3, but not 3 to 1. That's what we need. So how to do that? Just make the middle segment very short. So if you make the middle segment very short, that means that the fuzzy particle wave function will have a tail which go between 1 and 3. In other words, the Andreev levels are overlapping. Because you have spin-orbit coupling, you can split them in such a way that you get one Andreev level which is non-degenerated. It's not spin degenerate. If you tune the parameters properly, we'll have a Majorana zero mode somehow localized on the top and on the bottom between three superconductors. And now you can put a standard loops in that answering your question. So you can analyze that theoretically the key, there are coherence lengths which are E Fermi over delta, but now because we have this spin orbit coupling, then the Fermi velocity for spin up will be different from the Fermi velocity for spin down. Okay, should have said somewhere how, yeah. So that's actually very naturally happened in many different systems. Spin orbit coupling, it's actually, most of them will have different velocities for spin up and spin down. It's difficult to find material which have the same spin velocity. And this is, by the way, related. There's a lot of pressure phase. It's exactly the same thing, right? We have to look not on the velocity, it's not k divided by m, but k minus this effective phase that appears from the spin orbit coupling. So it's worked just like the magnetic field, but differently for spin up and spin down velocities. So this is exactly the same concept from a different angle. So you can analyze that. I will go quickly on that because that's the other stuff as well. You can analyze the position of zero Andreev level, which now will be not spin degenerate. They will have different velocities for spin up and spin down, and each zero indicate a topological phase transition. So this is theta and phi are these two phase differences, which we parameterize them in this way, phi and theta. So that whole thing is designed to be very similar to the situation in which you have one Josephson junction phi and another one with magnetic field. But now I have two parameters which are only phases of the superconductor. So there are these, depending on the differences between the speed and the velocity for spin up and spin down, there is this region of topological superconductivity that we expect to see. Now this device or suggestions open up many different ways to measure things. So you can measure the tunneling density of state just as usual. So this is what you expect. I wrote it there. So you will have a Majorana zero mode here, there, but now I can measure across the Majorana or between 1 and 2. So you have a whole set of prediction. The current between here and there will not see the Majorana zero mode, so there will not be a state at 0. But if I measure in this direction, there is a line at 0. So give you more options to learn to study and a whole new selection of materials. So it's not only indium arsenide and aluminium, it could be many different materials. It's work also on this TMD material, which have strong spin orbit coupling, but some of them do not have large G factor. And this is for mercury telluride. This is what we study. It's work for holes in germanium, which do have small G factor. So this is really, they have very strong spin orbit coupling with small G factor. So we had several suggestions of how to do these chains in planar geometry. This was a suggestion. The hope was that Amir will do the experiment. It was already 21. The nice thing about that, so how do you know that this is not an accidental zero energy state? And the key point here is this, you apply magnetic field and it has to be repeated every 2 pi. So you change the conditions of the system and you expect to see these zero energy states repeated again. So this gives you confidence. After all, in all this topology, it's very easy to get zero energy state. You have to tune some parameters. The key point is to show that it's robust. It's not sensitive to. So this gives you another confidence if you can produce this that it's indeed not just accidental. Accidental things will move when you apply that here and there. One is topological, so it's supposed to be there without. We can also implement this idea to create. Still there is disorder. We want to get rid of the disorder. So that work is Sam Scribano was constantly removed together with Andres Dahl and Carsten Flensberg. So the idea was to have one quantum dot which is connected to 3 superconductors with 3 phases and another one. Then you can tune the parameters so that you separate by 1 and 0 mode in this dot, and in this dot. So this is a quantum dot with Andreev level, no Coulomb interaction. And I think it may be useful because of this cross-talk, capacitive talk between dots, which I understand that this is also a main problem, right, Ramon? In this system that is based on Coulomb located. So and this can be, so again, you can tune now a chain. This is the hope that now you can tune a chain, get its localization, and there is this imaginary idea. These are the gates. We'll get one marijuana here, one marijuana there initially. And in this way, you can create the entire chain by controlling the Andreev levels by these gates. So the idea is that you measure 2 dots, you know the properties, then you tune them to the sweet spot, you measure the other 2 dots, you connect them, and in this way you create a chain which is to overcome the disorder by tuning many parameters. This is not the usual way we think, but this is the idea. Okay, there are only 5 minutes. So let me skip on that. So this, what happens is if you study 4 dot in this way, you will have now 0. This is a planar geometry. You will have 0 energy state here, and you can. So you will have 2 marijuana 0 modes, which are not spin. One level, which is not spin degenerate. You can couple between them in such a way that you get 2-dimensional topological superconductivity. Then you expect to see this marijuana modes propagating on the edge. So in the sense of time, I want to discuss the experiment that was done for the 2-dimensional. So this is a different model, not what I described today, which will work in many different materials. But this Fuenkain idea that on the surface of the topological insulator, we put superconductor, you get a p-wave superconductivity. So the main thing that bothered me when I saw this idea is that you have these edge modes, but the edge modes continue. So you have to say, where are they? So if you have a Josephson junction, like in this topological insulator continue somewhere else, then you will have these edge modes, and you have to think what happened with them. So then we came with this idea, in discussion with Philip Kim, to do. So this is the topological insulator. The edge mode will be coupled to this part of the topological insulator. we have this idea to think about Corbino geometry. So these are just experimental suggestions. So you measure the current, so from inside to outside or from outside to inside, and here you don't have this. So we expect to see a Majorana zero modes propagating on the edge here and on that edge as well. And this is what controls the coupling of between the two superconductors and the Josephson junction effect. Now, so what you expect to see? So usually in just junction, when we apply magnetic flux, we expect to see this Van Hofer pattern. But now in Corbino geometry, the flux will be quantized. So you kind of probe or only the phi equal to 0, phi equal to 1, 2, 3, and 4. So you expect to see something like that. That's what you expect to see. 1, then 0, nothing. You see, and it's appear to be, then if it's topological or not topological, it's the same story. So it's kind of doesn't give you any indication if it's topological or not topological. And then we came with this idea. So people also defined this eta, which is the superconducting diode effect, the difference between current from in to out and out, inside to outside, from outside to inside. And we define this superconducting efficiency, diode efficiency eta. So then we came this idea, don't think about circle. Actually, this 0 is because of circle, but have this geometry which is a square. So I'm skipping the calculation, but let me show you the results. So this is for a ring geometry, 1, 0, and for square geometry, there are 4 coordinates. Reappear. But you see that the numbers are very small. This is because of this, the Van Hofer pattern goes like 1 over 2 pi and so on. So this is why this is already 10 minus 1. And 8 is kind of a weak effect, but it's there. And if you study the topological case, so what happened? Okay, skipping that. What happens is you expect that to see an even odd effect. The point is, so the differences are really tiny. It's all very weak effect. But you see that here the periodicity is 2. One is really small, but it's 2. No, it was a weak effect. It was disappointing from our point of view that it was very small effect. But so okay, let's see what happened in the experiment. So you really see nicely that you go from the ring geometry, basically 1, nothing, and for the square, there is something at 2, but it's especially 1, 4, 8. So that was kind of showing that we have some confidence in the system. And then that came from the experiment. They said, let's study this superconducting diode effect. And they saw this even odd effect. So you see that delta I is the difference between in and out current is positive, negative, positive, negative, positive, negative, and that's kind of repeated in the circle and in the square. So this is kind of universal behavior. So apparently, the superconducting diode effect is very sensitive to this effect, and we did study that also theoretically. So the basic idea is that when you apply magnetic field, you can have two. The inner circle will not be affected by the magnetic field, kind of outside of the circle. It don't go around the magnetic field, but the outer ring, encircle magnetic field. So it changed the boundary condition from even to odd, and that kind of why you expect to see this even odd effect. So that's what happened to the dipole efficiency. Just very easy to get this. Can't avoid it. It's a very strong effect. Why we try many different models, and you cannot get this even odd effect in standard superconductor. You have to tune many parameters. Yes. Done with time? Yeah. Okay. So there were two control experiments. one on graphene, no even on the fan, and one on Fraunhofer, no even on the fan. So,
What is the nature of tellurium device?
yes,
Why is tellurium there?
I think
Tellurium
it's,
is a very special system. It's,
okay. I thought back, I think it was the proximity effect was so. But you ask me why?
large spin orbit system.
No, all the spin orbit stuff is all come from the topological instrument.
Tellurium also has.
So it's helpful, but it's not necessary.
It's non-central symmetry.
I think it's not crucial, but crucial for details of the proximity. But from the symmetry point of view, it's sufficient to have the moment that I have topological insulator, I put S-wave superconductor with standard, it still should give you topological states. So tellurium was used for the experimental consideration. But it's not, I don't need a spin orbit practically, at least from the theoretical. Maybe practically give you some addition.
The discussion preparing for this afternoon, but maybe if there are other questions. Yes.
Right. You were mentioning something about the role of spin on the propagating branches on the different velocity. How critical is what you see? How strong does it depend on the fact that you could actually have differing velocity in your branches?
Yeah, so I had this graph. Once again. Here you see the difference. So the difference with velocity will different Taiwan, X-I2. So if they were equal, this area would be 0. And if they are very different, then one of them is, very small. So we saturate on that. So it's determine the region in which you have topological secret. You need a difference. If they are equal, the Andreev state will be the degenerate, both for spin up and spin down. And how much is the gap and so on, that's dependent on the velocity. Okay.
So regarding this cylindrical geometry, what was your theory at first, if you would do microwave spectroscopy on kind of individual superconductors, there you could do kind of like multi-terminal microwave spectroscopy. I would imagine that this would become non-controllable. So that, let's say, the transmission from 1 to 2 would be different transmission.
Yeah, yes.
And now I'm trying to figure out, can this be done also in this planar geometry? Most likely, yes.
I didn't think carefully about it, but I think it's.
But this might be
do that microwave experiment.
That might be an interesting way to probe to my run.
Yeah, yes, absolutely. Volley. Yeah.
Yes.
Supercurrent flow in a circle and a square of very different local bands. Like there's
Right. That's why you get this force harmonic. Yes, that's the point. The corners give you the phase of, usually the phase evolve linearly in a circle. The phase evolve linearly with the angle. The phase of if I have a flat, the phase difference between the inner and the outer will evolve linearly with the angle, and so it will be a linear function.
yes, but also
Now near the corner, it's the phase advance faster, so it's and that's the reason why you have this every fourth.
and also the current density.
Yes. Yeah. No, that's the key point. Yeah. So just let me put it concluding slide. I didn't have time to get. No, it's okay. We can discuss everything. So there are these experiments that I didn't have time to going on. And this is the discussions of how to probe in edge mode. There are several ideas of how to do that. I can discuss it in more detail, but what I wanted to tell you is that this P-wave superconductor also have the word all day about about the superconductor insulator condition, that the insulator side of the P-wave superconductor is a very interesting object, is an object that system that does not conduct charge, an insulator, but conduct heat only on the edge. So this is what will be a signature of really exotic phases of time.